You have the question.
Okay. Now,
Okay, look.
let's talk about number 7.
But do we need to have that?
Because if you're, one of the most important things you've got to be able to do is stoichiometry. We are going to do a lot of it, okay? So, let me kind of give you what I'm looking for as an example on 2B. Number 1, I've already given you the balanced equation. If this is a synthesis reaction, aluminum is reacting with chlorine to produce aluminum chloride. So, if I were to do that part B, how many grams of aluminum chloride can be produced with 1.08 grams of aluminum? So I would start here, and I'm going to go 1.08 grams of aluminum. So here's the golden rule of stoichiometry. Whatever units you have here are what the units are that you put down below. There is no exceptions to that rule whatsoever. None. Zero. Zip. But this is why you have to say, hey, what do I got? Because if you just put 1.08, I don't know what that is. Great, you wrote down 1.08, good for you, Skippy. You wrote down a number. What does it mean? I don't know. Put down 1.08. So I'm going to put grams of aluminum here. So what's the first thing I want to convert those grams of aluminum into?
Moles.
Moles. So 1 mole of aluminum is how many grams?
26.98.
So for this, you can generally just round to like the nearest tenth. So you can just use like 27.0 on that grams of aluminum, but at least go to tenth. If you want to go to hundredths, that's fine. And that's especially important when you get into something like chlorine. So chlorine is 35.5. Don't round chlorine down to 35. Don't round it up to 36. Keep chlorine as 35.5, okay? Because otherwise you get numbers that are going to be off. So at this point, if you didn't do anything else, what would you have? What units would you have?
Moles of aluminum.
Moles of aluminum. If you do nothing else, you stop right now, you're just going to be in moles of aluminum, okay? So you've gone to the periodic table, you've done this. Now, let me give you a quick refresher. If you have 1 mole of aluminum, you have 27 grams. How many aluminum atoms are in that 1 mole?
6.02.
Avogadro's number, 6.02 times 10 to the 23rd. Now here's the irony of calling this Avogadro's number. Avogadro never actually found the numeric value of this. He just proposed the concept, okay? He never actually found the number. Like Isaac Newton never found the universal gravitational constant. So, but here's the question, and I ask this in all sincerity. Why is Avogadro's number 6.02 times 10 to the 23rd? Why isn't it 12 or a million? Why is it that specific number?
So many atoms are in the thing. I don't know.
The mole. The mole? How many atoms are in a mole?
The mole. But
But why is it that specific number?
doesn't it have to do with, like
12 grams. Isn't it?
hydrogen or something?
Wait.
It's based off carbon.
Jacob?
Carbon?
It makes it so that the atomic unit weight of the particle or the atom is the same, is like converted into grams at a mole scale.
I see what you're saying.
Yes, you're about 80% of the way
Yeah.
there.
Proportion.
Yeah.
Proportionality.
No.
Bro, I got like one.
Don't listen to Charles.
Okay. Let me
Anyway, I'm
give you
wrong.
a quick history lesson on relative atomic mass. So the concept of relative atomic mass was actually really first started used in like the 1800s. Because they didn't have the capacity to measure the mass of a single hydrogen atom or a carbon atom, okay? They didn't have that capacity. So what they did is and the reason they picked carbon is because of the fact that pure carbon is really easy to produce. Literally, you take a green bean, throw it in the oven in a vacuum and heat it up, the green bean is going to turn into a black carbon, okay? That's it. So do you want pure carbon, bake a green bean. you're gonna have a black pure carbon substance, okay? And so that was easy to produce in different labs around the world. Oh, hey, let's use carbon. And they got lucky and they arbitrarily said, we're gonna call that a relative atomic mass of 12. They had no concept of protons or neutrons at this point, okay? They hadn't been found yet, okay? Protons and neutrons had not been found. They said, hey, why don't that carbon be 12? So then they said, okay, well, let's compare that to hydrogen. So they assigned hydrogen a value of 1. So what that means is that if you have the old style pan balances, if you put 12 hydrogens on one side, that would balance out 1 carbon atom on the other. So again, they did not know the actual mass of the values. It's a relative mass. That's all it is, okay? That's all they had to go off of because they did not have the capacity to measure the individual mass. So then they said, well, working in the lab, we're never going to measure out like 5 carbon atoms. We're going to be dealing with larger quantities. So they had, at the time, this is important that you understand the sequence, they had relative atomic masses, okay, which is what they used as one basis to do the initial arrangement of the periodic table, okay? I mean, Russian and Mendeleev kind of came up with that first setup based upon chemical properties and relative atomic mass. The beauty of what he did is that he left gaps. And he says, hey, I think there should be some elements that we could find to fill these in. So they said, okay, and this was the debate. Well, what measurements are we going to use? Are we going to use pounds? Are we going to use grams? Are we going to use kilograms? What are we going to use? So they played rock, paper, scissors, and the scientists that wanted to use grams won. So they said, okay. So this is kind of what Jacob said. So the relative atomic mass of carbon is 12.0 AMU, atomic mass units. So here's what they did. True story. They said, screw the AMUs. We're going to put grams on the end of it. That's literally what they did. So they marked out atomic mass units and they said, we're just going to call these grams. They could have chosen pounds. They could have chosen ounces. They could have chosen kilograms. They just said, we're going to make this grams. Cool. Great. 12 grams. Now the question being, well, how many atoms is that going to take? Obviously, it's going to be a lot. So basically what they did is they said, hey, we're going to start piling in carbon atoms on a scale. So we've got a panel. We're going to start adding carbon atoms. And we're going to add carbon atoms until the reading on that scale is exactly 12.0. And then we're going to count how many atoms it took to get to 12. Okay? And they counted those and they said, oh, that took 6.02 times 10 to the 23rd. And then they said, oh, let's do that with magnesium. Oh, magnesium was 24.3. So then they said, okay, how many magnesium atoms is it going to take to get to 24.3 grams? Lo and behold, it took the exact same number of particles. Okay? So the reason that it's 6.02 times 10 to the 23rd is because it takes that number of particles, the total mass of those particles, to equal the relative atomic mass in grams. Now in physics, we call it a kilomole, which sounds kind of barbaric. But in physics, Avogadro's number is 6.02 times 10 to the 26th. Because instead of 12 grams in physics, we use 12 kilograms. So it takes 1,000 times more atoms to get 12 kilograms than it does 12 grams. Cohen.
How do they count those atoms?
It's probably one of the most difficult things that you can do. You can't count the individual ones. So if you ever do the lab, like one technique you can do, like with oil, is that you take a droplet of oil and you let it disperse over a surface area, and then if you know the volume of that, and then you can let that disperse out, and you can do some like hocus pocus, and you assume the size of the droplets, and you can kind of get the number from the biggest experimental error I ever had was trying to find an experimental values for Avogadro's number, and I was off by like 1,200% or something like that. So, no, it is, it's tough to do, because you can't count the individual ones. So, that's why it is what it is. It'd be easier if it was like 100. Well, here's the problem, if you stack up 100 carbon atoms, it doesn't add up to 12 grams.
Dang
The
it.
number would be easier.
Dang it.
If it did, those carbon atoms would be really big.
And really
I
funny
see no
looking.
problem.
Oh, I know, but I'm just saying. Okay, anyway, so back to our stoic story. So at this point, we're in moles of aluminum. What do I want to end up in?
Something.
Moles of aluminum chloride. So I got to go from moles of aluminum into moles of aluminum chloride. Anytime you do a mole-to-mole conversion, where do you have to look? The periodic table or the balanced equation?
Balanced equation.
Balanced equation. And that ratio in this situation is
2 to 2.
2 to 2, right?
Okay.
2 to 2.
Wait, which one?
Who said 3 to?
Charles.
Now, if I stop right now, what units do I have? Moles of aluminum chloride. What do I want? Grams of aluminum chloride. So I'm going to put moles of aluminum chloride down here. 1 mole of aluminum chloride, and then I'm going to look up the molar mass.
We were looking at the first one.
So the answer to 2B should be between 5 and 7 grams. Okay, Gabson? Your answers to 2A and 2C should start with a 1. Your answers to 2A and 2C should start with a 1.
Okay.
Okay? Good with that? All right. So let's talk molarity. So people make molarity problems difficult because they forget one simple thing. And that's molarity. And if you remember this, it's really not that difficult. It's just moles per liter. Okay? That's it. But here's the problem. Do the scales measure in moles?
No.
No.
No. The scales measure in
Grain.
grains. Okay? That therein lies the problem. So if you look on 2A, here would be the situation. I give 1G 45.87 grams of nickel 2 nitrate. She dissolves it in 250 milliliters of water. Hey, what's going to be the molarity? So at the end of the day, she needs to take some number of moles and divide it by some number of liters. Okay? At the end of the day, that's what you need to do. Okay? Now, if you're a divide and conquer kind of person, you can take the grams, the 45.87 grams, convert that into moles and get that number. And then divide that by 0.250 liters, there's your molarity. Okay? It's cool, right? Now, your other option, you go, oh, Burkamp, I like stoic. I'm personally a fan. So I would go 45.87 grams of the nickel nitrate, come down here and put grams of nickel nitrate, and that's going to be 1 mole. And then I'm just going to divide by 0.250 liters, and then I'm just going to do it in one step. So I know my mass. I'm going to put the molar mass down here. That's getting me my moles on top. I divide that by the volume in liters. Winner, chicken dinner. Okay? But no matter what, how you do that, your answer to 8A should be very close to 1. Good?
Yeah.
No one's screaming, going, this is bad.
Wow, you're so close.
Now, let's talk about what? What?
I've just been, my calculator is like basically dead, so I'm just kind of like writing it down, but I don't actually have any numbers for anything. Charles was making fun of me, and I threatened him.
No.
I'm gonna make fun of you. You're my friend, Cullen. I wouldn't want to hurt your feelings.
I feel like it has something to do with the fact that I broke your
That's
pen.
Okay, now, let's talk about 8B, okay? So this is gonna be an important concept that you get. But I want to explain it in terms of cheese sandwiches,
Now
okay?
We're speaking food, this one.
So
That smells very good.
and we're gonna use this analogy a lot. So a cheese sandwich is made from 2 slices of bread plus 1 slice of cheese to make B2C. So there's the synthesis reaction to produce a cheese sandwich, okay? So that's the synthesis side. So here's the story. If I have in a bag 10 sandwiches, okay? And I put those in the bag, and then I shake it up, okay? So I've got, these are not grilled cheese, these are just cheese sandwiches. I put them in the bag and I shake up the bag, right? I do a disassociation. I cause them to disassociate, to come apart. What would be the concentration of bread within the bag?
2 to 1 cheese.
Yep. So if I have 10 sandwiches, how many slices of bread would I have in there?
20.
20. And you can do the stoic. You can go, okay, for every 1 cheese sandwich, I get 2 slices of bread. So the concentration of my bread is going to be twice that of the sandwiches. Okay? Makes sense. Go with it. Now, when you look on 8B, first off, you have to have the formula for sodium sulfate. So, Sydney, what's the formula of sodium sulfate?
Na2SO3?
Nope, close.
4?
Na2SO4, right? So here's the point of this equation. When this stuff dissolves, how many sodium ions are you going to get out of this? So you're going to get 2 sodium ions to every 1 sulfate. So if you know the concentration of the sodium sulfate, what's going to happen to the concentration of the sodium ions?
It's going to be twice.
It's going to be twice as much, just like the bread, like the cheese sandwich analogy. So on 8B, you can find the concentration of the sodium sulfate. But because you get 2 sodium ions kicked out, that concentration is going to be twice as much. So here's how you can do this if you do the stoic. If you go 24.8 grams of sodium sulfate, Na2SO4, and then the molar mass here, and you get 1 mole of sodium sulfate. Now, here's the story. You want, and this is why you have to get in this mindset of paying attention to the units. You want the concentration of sodium ions, which means you need the moles of sodium ions over some number of liters. At the end of the day, this is what you have to find, because this is how molarity is defined. So, if you stop right now, you have moles of sodium sulfate. But I know that for every 1 mole of sodium sulfate, I'm going to get 2 moles of sodium ions. That's where the stoic becomes part of this equation. Then, at the end, I just divide by however many liters that I have. So, that molarity on 8B would make a fairly decent GPA. Not horrible, not great, but not bad. Okay? Don't point at me.
I wasn't pointing.
Yes, you were.
You don't need to break your other pencil?
No. What did that pencil ever do?
Because I fly.
On number 8C, this is,
Sorry, Kevin.
So it's Addie's fault.
Yes.
It's gone.
On eight C, this is what you're gonna do a lot. Like, I'm gonna say, hey, here's the solution that you all need to prepare. So this is just basically the reverse of what you have to do, because scales measure in grams and not moles. So your answer to eight C should be around 30-ish.
I can't count that high.
Not my problem. Borrow Charles' toes.
Alright, start now.
Wait, the three of us, we have 30, we have enough.
This
We're
little.
good?
Toes, only 30
Morgan's doing, I'm having no part of this.
I'll
Start your team.
But how would you handle minions, though?
40?
They don't really have
Check
to.
on these.
They have 3
49.
Oh.
You have 50.
8D should be less than 1. A lot less than 1.
80?
Yeah.
8D should be less than 1.
What did she think I said?
Okay, all right.
Look what you.
Okay, so let's talk about the acid-base part of this. This is the one that kind of gives me the most concern. But it's a bigger picture. So if you start on number 9, you have 0.015 molar solution of hydrochloric acid. So this is why you have to know your strong acids. Hydrochloric acid is the quintessential idea. So I'm going to spend a little bit of time with this because this will pay off dividends later on. Because this is a strong acid, what happens is when you put hydrochloric acid in water, technically what it forms is something called a hydronium ion and a chloride ion, okay? So when you see pH, there's 2 ways pH can be written. You can have pH with your hydronium ions, which also equals P times the concentration of your hydronium ions. So when you see pH, pH just means negative log, okay? So this is why you kind of got to know some math to do this level of chemistry. So, and we're going to deal with a whole bunch of different types of pHs or things like that. So in this situation, if you want the pH, you have to take the negative log of whatever you're going to have. Like we're eventually going to be talking about pKa, which means you're going to take the negative log of a Ka value. We're going to talk about POH, which is going to be the negative log of your hydronium ion concentration. So the negative, P just means negative log, and then you're taking the negative log of whatever you have after that. So because this is a strong acid, so here's what happens on a molecular level. The hydronium, which is just a proton, and then the chlorine, they come up to the water molecule. Now, we need to understand the structure of water, because that's going to play a very important role in this whole equilibrium concept. So if you look at the structure of water, how many valence electrons does oxygen have?
2. No, 6. Sorry, it
6.
wants 2. It wants 2 electrons.
If you're not sure, count across. Find oxygen. Count across. It has 6 valence electrons. So it has 1, 2, 3, 4, 5, 6. How many does it want?
2.
It needs 2 more to be at 8 because it wants to be cool, okay, like neon. So the hydrogen comes along and says, yo, I've got an electron. Cool, now it's up to 7. So now it still needs 1 more, so you get this. We'll spend more time talking about this, but for now, understand that oxygen has these unbound pairs of electrons up here. And this makes this end of the water molecule very negative, okay? So the oxygen end of the water molecule is extremely negative. because it has this dome of electrons around it. It's a dome of negativity, okay? Now, the hydrogen is down here going, dude, man, we're protons, okay? But we've lost our electrons. So if you have a proton and an electron and you lose the electron, what's the only thing you have left? Protons. And what charge do protons have?
Positive.
So the hydrogen end of the water molecule is positively charged. So that's what makes water such a great solvent, is because of its polarity, okay? Technically, it has what we call a dipole moment, which we'll talk about later. Dipole moment just means that there's a region of unbalanced negative charge, okay? So it has a dipole moment. So basically what happens is this. The HCl comes along and it says, there's a water molecule. And it has to make a decision. Do we stick together as HCl, or do we separate, go our separate ways, and bond with the water? Okay, that's the decision that it has to make, okay? So the hydrogen goes, dude, chlorine, you're kind of naked. No, I don't like you. You're cool. It's HCl. We're a famous acid. But quite frankly, I'm more attracted to the water molecules. So the chlorine says, fine. So the chlorine end of this, because of the fact that it's negatively charged, goes down here to the positive end of the water molecule. The proton is left over, and it's kind of put out at this point going, oh, you traitor. Fine. So the proton that's left over comes up here to the positive, to the negative end of the water molecule. So once it does that, this is why we write it as H3O plus. So H plus and H3O plus, and from a chemical perspective, mean the exact same thing. Okay? So H plus, H3O plus mean the exact same thing. Technically, the H3O plus is more chemically correct because that's how it is actually existing on a molecular form, okay? So you don't ever have just a proton floating around. It's like, who are you? I'm Paul with the protons. No, okay? It's always going to be attached to Wally the water molecule. So we shortcut it and we talk about just H pluses, but in reality, it's attracted to a water molecule, okay? So, because hydrochloric acid is a strong acid, and if you, and I need honest answers, has everybody seen what we call a Rice chart?
What?
Okay, that's what I needed to hear. Blanks, I can live with blanks. Now I know I have to fill in the blanks, okay? So, a Rice chart stands for the reaction, the initial conditions,
Okay. These, yeah.
change,
I remember these now. We're good.
I was like.
Miss
and
said.
equilibrium.
Miss
What did Miss Hutt call it?
You're like C4 change at BCA tables.
Oh,
I think.
yeah.
Same idea. Or I'm gonna call them Rice charts, okay? So basically what it allows you to do is to keep track of what's happening in chemical reaction. The most important part of this, without fail, is the reaction. If you do not know what the reaction is, you cannot do anything else. Okay, you are dead in the water right from the beginning. Okay, nothing is going to make any sense at all. You are going to live and die by Rice charts. Get used to them, embrace them. Okay, they're amazing. So in this situation, I have hydrochloric acid in the presence of water, and that's going to form hydronium ions and fluoride ions. Okay? Now, I could care less about the fluoride ions. They're not part of the story right now. Okay? Because the fluoride ions aren't something we're going to worry about. So that's my reaction. HCl is going to react with water. I'm going to form hydronium ions and fluoride ions. So my initial is going to be what's the molarity at the beginning. So you're told that you have a 0.015 molar solution of hydrochloric acid. I don't care about the water, it's not part of the story, okay? What I care about are the concentrations of these ions over here. So initially, I'm going to assume that those start off at 0. So I'm going to say, okay, I'm going to put HCl in here, and I know that concentration, I'm going to assume everything is going to be 0 on the other side. I don't have anything over there. Now, because HCl is a strong acid, what that means is that it basically 100% ionizes. It goes, fine, hey, we're out. We're going to split up. We're gone. Done. Gonzers. So the change is that I'm going to lose all of that. Okay, all of that goes away. It will none of it will exist as HCl. But whatever I lose here is what I have to gain over there. So this is going to be plus 0.015, plus 0.015. Check my math, but if I subtract this out, I get 0. This is 0.015, and this is 0.015. So this is what I'm after to calculate my pH. Okay? So because HCl is a strong acid, whatever the concentration of the acid is going to be whatever the concentration of the hydronium ions are, because it's a strong acid. Now, later on we're going to get into weak acids. Weak acids don't do this. Weak acids, only a small percentage of that ionizes. Strong acids, completely ionize. So here's the dichotomy between strong acids and weak acids. Strong acids have exceptionally weak bonds between the proton and the anion. So if it's a strong acid, there's basically no bond to hold them together, and the water shows up and they go, hey, we're out. See ya. Love to chat. Gotta go. Okay? So if you can put this in terms of prom's going to be coming up. Prom season's going to be coming up. So if you and your date are a strong couple from a chemistry analogy, as soon as you get to prom, you're going to ionize. You're going to go with your friends, your date's going to go with your other friends. Hey, we're out. Because you show up, we'll take pictures, click, click, okay, gotta go. So when you get to prom, you are going to completely ionize. Because there's just enough bond to get you to prom, but as soon as you walk through the doors, gotta go. Busy, busy. We'll catch you later. Okay? What? Yeah, you're like,
I'm trying to listen to your explanation.
did it work?
Sure.
Go with it. Okay. So, strong acids, humor me. Say a word. So, strong acids, when you get to prom, ionize. They completely separate. Okay? What's going to happen? Now, when you get to this one, so all you're going to do is define the pH. You're going to take the negative log of 0.015. Okay, that's all you have to do. Punch it into your calculator, negative log, boom. You should get an answer around 2. Okay? So technically you're going to get 1.82. When you do pH values or pOH values, listen to me. When you do pH and pOH, you want 2 numbers to the right of the decimal place. So that answer on 9A needs to be 1.82. You need 2 numbers, even if they're zeros. Whenever you do pH or pOH, you need 2 numbers to the right of that decimal place. Okay? Always 2. No exception. I don't want 3, I don't want 1, I only want 2, because all of our instruments, that's what they're going to measure in, is 2 places to the right of the decimal place. Okay? That's all you have to do.
I'll forget that.
Now, when you get to the next one, I've given you the pH of 4.57, and I want you to find the hydronium ion concentration. So, if pH equals the negative log of your hydronium ion concentration, how do you undo a negative log?
Someone do 10.
Yeah, because we're assuming this is a log-based 10 system. So if I've given, so I won't be doing anything weird like log-based 2 or weird stuff weird like that. So to undo this, what you're gonna do is you're gonna take 10 and raise that. In this case, you have a pH of 4.57. So you're gonna take 10 and raise that to the negative 4.57. That's how you're gonna undo that logarithm, because it's a base 10 system, okay? If you ever get molarities of like 14 or 15 or 12, you have done something horribly wrong, okay? Molarities tend to be, especially with acid bases, tend to be really small numbers. What time are we done?
Like 08, I think.
Oh, no.
09?
Oh, 09, you were close.
Okay.
I was close. Hey, good guess.
So your answer to that one should be 10 to the negative fifth. Now, when you get to the next question, so if you look on, let me see your green sheet, Christmas. You gotta use the power of the sheet. So notice on right here that you've got, like, for example, pH equals negative log of your hydronium ion concentration. POH equals negative log of your hydroxy. You don't have to memorize it, it's right here. Now, notice down here you've got a couple of things that are important. First off, you've got KW
Yeah.
equals KA times KB.
I remember that.
What?
So, we'll explain what this means.
No, I remember, right? That's the pH of water equals pH of your acid times the pH of your base.
Yes, or added together, not
Or added together.
So here's the importance of this. This KW, okay, which is at 25 degrees Celsius, but that's, you just always assume that you're 25 degrees Celsius. Notice on that KW, that also equals your hydronium ion concentration times your hydroxide ion concentration, which equals 1.0 times 10 to the negative 14. Now, conveniently, Mother Nature wanted this to work out relatively easily. At 25 degrees Celsius, when you multiply these two concentrations together, you get a nice number of 1.0 times 10 to the negative 14. It could have been 3.52 times 10 to the negative 25th, okay? It wasn't. We got lucky, okay? 25 degrees Celsius, hey, this is the hand that we're dealt. It worked out nicely. We didn't get to choose this. It's just the hand that we were dealt. And it's cool. So what that means is if, like, say for example on this one where I've given you the hydroxide ion concentration, you want to find the hydronium ion concentrations. So these two numbers multiplied together always equal 1.0 times 10 to the negative 14. Amongst the things that irritate me, do not tell me, oh, water equals 1.0 times 10 to the negative 14. That is not water, okay? It's technically called the auto-ionization constant of water. So if you want to annoy me, it's like saying decelerate in physics, okay? Don't tell me, oh, water is 1 times 10 to the negative 14. Shut up. It is not. It's the auto-ionization constant. But what that means is that as one number goes up, what has to happen to the other one? It has to become smaller. Now, what that also means is that if I take my pH and add it to my POH, I'll always get 14.
Neat.
So at water, if it's neutral, the hydronium ion concentration, 1 times 10 to the negative 7th, times 1.0 times 10 to the negative 7th, equals 1.0 times 10 to the negative 14th. So if I take the negative log of 1 times 10 to the negative 7th, I get 7. If I take the negative log of 1.0 times 10 to the negative 7th, I get 7. So this is why your pH plus your POH always add up to 14. Okay? All right, I know Southeast, you've got to go. We will finish the rest of this discussion tomorrow. So hopefully that gives you some broader idea on what.
I'm doing so well.
Kevin, can you stop you on camera? First have that again.